vectors with respect to which you want to express the input. So if the input, if the string of neuron values you consider a vector, then being given many different inputs means being given many different vectors. And the question is, what is a good choice for a number of vectors to represent these inputs with? Okay, so when we went through the mathematics of this, we arrived at an object that is really important in this game, and that is you have to somehow be able to talk about the statistics of input vectors. And taking a page out of the quantum mechanics textbooks, let's call these vectors psi. So these are the input vectors. Each new psi will be a different input vector. And psi m will be one of the components of this vector. So m would range over the number of input neurons that you have. And what we figured out is, in order to find the best choice for the weights in this neural network, in this linear autoencoder, what matters is not the average of the vector. That could be trivial. For example, it could be 0. I will assume it to be 0. But what matters is something like the variance, or more particularly the cross-correlation matrix. So here I take some psi m, and then maybe some other component psi n, and in order to make it similar to quantum mechanics, I will even allow for complex valued vectors, so that's why I put a complex conjugate here, but this is not so important for the present context. Anyway, we multiply two different components of this vector, and then we average over all possible input examples. I mean, this particular psi m is a component of this particular input example, but now I will average this quadratic form. I will average it over all kinds of input vectors. And so this is obviously some statistical measure that describes your distribution of input vectors. So for example, it could be that the different components of the input vector are always completely independent random variables, more or less, in which case this would be a diagonal matrix. So only if m equals n, then you would get a non-zero contribution, because if m equals n, what sits inside the brackets is obviously psi m squared, so this is positive, so this gives you something even after averaging. But for all the other cases with m is not equal n, then this would just average away to 0, because if m is not equal to n, by assumption we would say they are independent. So this could be a simple example. But in general they will not be independent. Even if m is not equal to n, this gives something non-zero, and then this is a very interesting and useful matrix to look at. And in quantum mechanics, this matrix is known as the density matrix, and it is used to describe exactly situations where your wave function is not quite certain. So you're talking about a statistical set of wave functions, for example, in thermal systems. So the wave function could be this, or it could be that, and so on, with different probabilities. And then you want to describe this situation of uncertainty by using a density matrix. Okay. And the claim is now that knowing this Hermitian matrix is already good enough to understand what will be the optimal linear autoencoder for this case. And the claim is, and it would take a few lines, the claim is you just need to take this matrix, which by the way is Hermitian, and you need to diagonalize it. And you look at the eigenvalues and the eigenvectors, and now you just keep the eigenvectors with the largest eigenvalues. They have a meaning, they are, so to speak, the most important eigenvectors in this game. For example, if your Hilbert space is 10-dimensional, let's say, so the vectors are of length 10, but if you only, in this statistical averaging, if you only were ever to encounter two different vectors, yeah, because 50% this vector, 50% that vector, no other vector, then it would turn out that this Hermitian matrix would only have two non-zero eigenvalues and the rest would be 0. And then keeping those two eigenvectors would be absolutely enough to describe everything. And so just to give a graphical representation of this, if I have a 2D Hilbert space, then of course everything is easy because I can draw pictures. And then let's say the first component of each vector I draw on the horizontal axis, the second component I draw on the vertical axis. And then for each vector that I'm talking about, I may put a point in this diagram. And now if I were to do the average that I just described, this psi m, psi n star average, in order to get a density matrix, what would be the meaning of this density matrix? Well, it turns out that if you have this point cloud of vectors over which you want to average, then if you get the eigenvectors of the density matrix that I just defined, they would point exactly in the two major axes of this kind of elliptical point cloud. So if it's more spread out in this direction and less spread out in the other direction, so these would be the directions of the eigenvectors. Yeah? So it's similar to classical mechanics. If you want to calculate a moment of inertia and these would be mass points, then again you could diagonalize the tensor of inertia and you would find such eigenvectors. Okay. And so, yeah, this is it. So this is the so-called principal component analysis. So take some statistical set of vectors, calculate this kind of matrix, which tells you how the components of the vectors are correlated, and calculate its eigenvalues and eigenvectors, and only keep those eigenvectors with the largest eigenvalues. Somehow these will be the most important if you want to represent any of these many vectors in terms of such a incomplete basis. Okay. And so this might have sounded a little bit abstract, but here would be an example of how to apply this to a set of pictures. And why not just take this database of handwritten figures from the MNIST example, yeah, where we want to do digit recognition. And so the typical examples you get, they are pictures that have 784 pixels. Okay, that was the 28 by 28. So these are my vectors. These are the psi. So the dimension of my Hilbert space is 784 in this case, because each image corresponds to a 784 dimensional vector. And then in this whole training set, I really have 50,000 of those examples, 50,000 different pictures. Some are the digit 3, some are the digit 5, and so on. And so, well, first of all, I want to prepare things by saying I don't care about the average. So I want to make sure that the average vector, the average of the vector components is just 0. So I simply subtract the average. I take all the training inputs. I sum over all the training inputs here. This would be summing over the first axis. So axis equals 0, which would be the axis that counts the training example. And then I divide by the number of training examples. So this first line just makes sure that I subtract the average. So we can interpret in the statistical way that I described. Okay. And now I just want to execute this this step. So I want to take the product of two of the vector components, and then I want to average over all the training examples. And in our case, it will be 50,000 training examples. And the funny thing is, in Python, this is just a single line. Yeah? So if you look very carefully at how the training inputs, or the psi essentially, is structured, they are somehow in the form of a matrix, so 50,000 by 784. And the 50,000, that's the different training examples. Now, it turns out if I transpose this matrix, then the 784 will become the first dimension. The 50,000 will now be the inner dimension. And then if I take the matrix product, I will sum over this inner dimension, which will be exactly the sum over the training examples that I need to carry out here, if I want to calculate the average. Yeah. And in principle, maybe I would want to normalize, so I would want again to divide by the number of samples, which I didn't do here. Okay, fine. But that doesn't bother me in the following. Okay, and now I take all the eigenvalues and eigenvectors of this matrix. So this is what happens here. So there's obviously a NumPy routine available for doing this. So I now have this 784 by 784 matrix. I get all my eigenvalues and my eigenvectors as the return of this return value of this routine. And that's it. So these are, they are already sorted in the sequence of the size of the eigenvalues. And now I can, for example, ask, what's the biggest eigenvector, the most important one, the one where the eigenvalue is largest? Well, since they are sorted, I will just take the eigenvector with index 0, so the first one. That would still be a vector of dimension 784, but I want to display it as a picture. So what do? Well, I can always reshape arrays in NumPy. So I can take this vector and I can tell it, well, please reshape this 784 vector into a 28 by 28 matrix, which I can display as an image. And so that's what I do. So I display this matrix as an image, and this then is a representation of this eigenvector. Yeah? So this is the biggest, the most important eigenvector, displayed again as an image. It does not obviously refer to any of the digits. It's somehow a mixture of everything, but it looks a little bit like the digit 0. Yeah? Maybe that's also because many other digits are also of sort of this shape. If you think of the 8 or of the 3 and so on, they will always look sort of like this. And if you are interested in how the other eigenvectors look like, this is how they look like. So you have this one, this one, this one. So none of them represents only a single training example. They are somehow a mixture, a smart mixture of all the training examples. Also, you should note they are all orthogonal to each other. So this one, it's not obvious maybe from the pictures, but if you think of the vectors and you take this vector, a scalar product with that vector, that will be 0, exactly 0. Yeah? And so now what you can do is you take any given training example and you try to write it as a superposition of these vectors. And you only take those eigenvectors with the largest eigenvalues because they seem to be the most important. And then the promise is that this will already give you a very good approximation to the actual shape of the of the training example that you looked at. And to prove that you can get the most information from the first few eigenvectors already here, I've plotted really all the different eigenvalues. So it's a 784 by 784 matrix. Therefore, there will be 784 eigenvalues. And what I'm plotting is the size, the value of the eigenvalue against the index. So if you just order them from largest to smallest, then you count from 0 to 783, I guess. And what you see here is that the first eigenvalues are by far the largest, and then it falls off very rapidly. Yeah? Which just means that, so here, for example, I say the first 100 sum up to more than 90% of the total sum. So what this means is, and maybe this would be a good homework, if you try to express some of the training examples as a linear superposition of these first 100, then the approximation will be very good. So to make it very precise, this quadratic cost function, the deviation between the actual vector and the vector that has been projected down to these first few eigenvectors, this quadratic cost function averaged over all training examples will be small. We chose them precisely for this purpose. Yeah. Okay. So that was principal component analysis. It really has nothing to do with neural networks. It is quite independent. But I try to present it here as what would result if you were to construct such a linear autoencoder and ask what's the best choice of weights. So we solved this problem here analytically because it was a linear neural network. We could do it. we could analytically try to minimize the cost function, and then we found, oh, we need to look at this kind of density matrix and get its eigenvalues and eigenvectors. But you could also do a numerical experiment. You could literally take this setup for a linear autoencoder and train it long enough on your samples, and then try to compare against what is the result of taking directly the statistical approach and getting directly the eigenvectors. Okay. Yeah, is there still some question about this part? It was a bit more mathematical, but I thought it's a good opportunity to discuss this since we were discussing autoencoders. And so what some people really do is, if you want to apply a neural network on a large number of, say, images, you can make the choice that you first do this kind of statistical analysis and do a principal component analysis and get the biggest eigenvectors, and then you always project your input image or whatever it is onto these first few largest eigenvectors, and you take this as input to your neural network. So then you have pre-processed it already a little bit. Okay. So if there's no more questions about this, I want to jump to a seemingly very different topic, but it's kind of related. Again, this is about unsupervised methods of extracting a lot of information from a large data set. So autoencoders are unsupervised in that I don't have any labels. And also what we'll discuss now will be without any labels. You just have a big data set. You have a feeling there's some interesting structure maybe there. Maybe there are some examples that are close to each other, and there are other examples that are close to those other examples. So how do you try to make sense out of it? And in contrast to what I just described, this will no longer be about linear algebra and eigenvectors and so on, but it's a nonlinear technique. And it's mostly about visualizing high-dimensional data. And so this comes up in many different contexts, but of course it also comes up for neural networks. Because if you give some input to a neural network and then you process this input, you want to visualize the neuron activations in some of the hidden layer. The problem is there are maybe 300 neurons in this hidden layer, so how do you even visualize this? You cannot plot a point in a 300-dimensional space and show this to people, so you have to have a smart way to do it. Okay, so this is what I say here. Often we would like to represent somehow, to visualize the neuron values in some intermediate layer, but there are so many of them. And so for a given input example, say there are 300 neuron values. Of course, you could plot them in some way, but what you really want to do is for the 10,000 different training examples that you have, each one of them should correspond to a point. Now, unfortunately, it would be a point in a very high-dimensional space, as many as there are neurons. And so you want to have a way to get down from this high-dimensional space down to 2 dimensions again. Yeah. And so now, of course, there are many ways to project down from a very high-dimensional space. Even just from 3-dimensional space, I can say that I project always along the z-axis, which means I only keep the x and y coordinates of any point. This is a way to project down from 3-dimensional space to 2-dimensional space. But it may not be very helpful because maybe there are points that are very separated in terms of their z-coordinate, but very, very close in terms of their x and y coordinates. And then once you project it down, you will not see that they have been far apart in the high-dimensional space. So maybe you would want to find a good angle along which to project things. And in some sense, this principal component analysis actually was about finding a good angle along which to project. But maybe you can do something smarter. Maybe there's a nonlinear way of projecting things. And I will later come to the example of the cartographer. So if you have someone who wants to draw a map on a plane, but that map should represent the planet Earth, which is curved, then you also have to find smart ways to project down, in this case, from 3-dimensional space to 2-dimensional space. And so now you wonder, okay, so what are the important characteristics that I want to keep? which are the features that this projection, this magical projection should fulfill. And so one of the most important features is obviously whether 2 points are close in this high dimensional space or not. Think again of neural networks, yeah? So if 2 input images give almost the same neuron values in some hidden layer, yeah, up to small deviations, then that means the neural network is of the opinion that these images somehow represent the same thing, obviously. Whereas if these neuron values would be very different, then apparently the images mean something different. So what you really want to have is you look at the distances in this high dimensional space, and if 2 points are very close together in this high dimensional space, you want to make sure that your projection is set up so that these points are also close together in this low dimensional space. Obviously, this will not always work, but the question is how well can you make it work? Okay. So, well, here's a first example. I said one of the simpler techniques of projecting down high dimensional input data down to 2 dimensions would be to take the principal component analysis that we just discussed. So you take the statistics of all the training vectors, you calculate this kind of matrix, this density matrix, you get the eigenvalues and eigenvectors, and in this case you would only take the 2 eigenvectors with the largest eigenvalues that are seemingly the most important. And then you could take every training example, every data vector you could take and project it onto these along these 2 axes, along the 2 eigenvectors, and you could plot the projections here in the 2-dimensional plane. So this would be component number 1 and component number 2. So projecting onto the 2 eigenvectors with the largest eigenvalues. And so this was here done for, again, the MNIST, the handwritten digits. Each point here represents a full image. Each point is a full image, one of those 50,000 training images. And it has been projected onto the 2 most important eigenvectors of the principal component analysis. And now, in order to see whether this makes sense, this technique, every point, which represents an image, has been color-coded. So the color means which digit was it? Is it a 3 or is it a 5? So these are the different colors. And so what we hope to see is if points have the same color, so they represent the same digit, hopefully they are also sitting in the same corner of this point cloud. Yeah? That would mean that this projection is somehow reasonable. Yeah? If it keeps together points or images that represent the same digit. And indeed, at least sometimes it seems to work. You see here the blue. I don't remember which digit the blue represented, but at least this is nice. And you can also see some trends in the other corners, say, I don't know, more reddish here than there and so on. So there seem to be some trends, but it's also quite obvious that only having the 2 most important eigenvectors is not enough. Yeah? To nicely separate this point cloud, you would need to go into a higher dimensional space, yeah, to separate these differently colored points that represent the different digits. So it's a start, but it's not yet very good. And so people have invented much more sophisticated techniques, which I want to talk about. And so the particular technique that is very popular that I want to introduce here is called tSNE. I say what that stands for later. But that represents a nonlinear projection from a very high dimensional space down to 2-dimensional space. And again, it has been applied here to the MNIST example. And again, each point represents one of the training pictures, and it's colored according to the digit that it represents. And you immediately see that this works much, much better. So the digits are nicely separated into clusters. Here's one cluster of 1 digit, here's another cluster of pictures that represent another digit, and so on. Of course, it's not perfect. Sometimes here you see some points of a different color which seem to fall into this cluster even though they should be sitting somewhere else. But it's much, much better than the principal component analysis. So what you could do, and this is without labeling, I have to remind you. Of course, we use the labels in order to draw the colors, in order to verify that this is a good projection. But even if we did not know these colors, even if we did not know the labels, we could still have done this projection. And we automatically would have discovered that there are clusters, and then maybe we would have looked more closely into these clusters, and then we would have understood, aha, they have all something in common, they represent the same digit, and so on. Yeah? For the digits, it's obvious, but maybe you're dealing with a very different data set, something from physical experiments that you measured some data, and you apply this technique, and suddenly you're starting to see these clusters, and maybe every cluster has a particular meaning that you can find out. Yeah? Okay. Well, okay, so that's the end result. The question is, how does one get there? And again, we need to specify what should be the objective of this projection. So what should it keep? What should it do well? And I already told you what is the objective. It is to make sure that if 2 points are close in high dimensional space, they should also remain close in the low dimensional space, as far as that is possible. It will not always be perfectly possible. Yeah? So in the end, we have to introduce some weighting. We must say, okay, for us it's very important that if they are really close in high dimensional space, then they should definitely be close in low dimensional space. Whereas if they are kind of further apart, not that close in high dimensional space, then we don't care anymore. Okay, so on the left, I represent our high dimensional space, n-dimensional, and these are two. Each point is one of the points in this point cloud that represents the training examples, let's say. And I want to find a projection, that's this red arrow, that gets me down to 2 dimensions. And I want to make sure that these 2 points that have been close still remain close. Yeah? Well, so the question is how to do this. Now, I'm trying to find some function from this high dimensional to this low dimensional space, and I have an idea of what this function should be doing well. This is a similar situation to neural networks themselves. And for neural networks, we introduced a cost function. We defined something that we want to minimize. And so let's do the same here. We want to define something that we want to minimize in order to exactly get this behavior. Just to remind you, we will never be able to do it perfectly. That's known as the map maker's dilemma. So the Earth is curved, obviously. And so there is simply no way to take the whole surface of the Earth and put it into the plane in such a way that all the distances are exactly preserved. This is simply impossible. If it were possible, that would be a sign that the Earth is not intrinsically curved. So for example, if the Earth were a cylinder, which it is not, then we could unroll the cylinder and turn it into a flat piece of paper. So that's possible without tearing it apart or stretching it in any way, and the distances would be preserved in this way, so that would be fine. But the Earth is a sphere, and you can try it with an orange. So if you want to make it flat, you have to tear it apart in many spots, and even then it will not be completely flat. Yeah? Or in a higher flying language, I mean, this is all in principle encoded in the metric, which exactly gives us the distances at close separations. And simply by knowing the metric, you will be able to read off whether you have an intrinsically curved surface that can never be flattened into a plane, or whether you have something like a cylinder which can easily be flattened into a plane. And the Earth is definitely a sphere. Okay. So now let's introduce this cost function that I talked about. So we should, we should calculate something like the distance in the high dimensional space between 2 points, xi minus xj, and then some distance, however you calculate it, maybe just using Pythagoras. And then also calculate the distance between the corresponding projections in the low dimensional space. So xi is mapped onto yi and xj onto yj, and then I take their distance in the low dimensional space. And then I want to compare these distances. And again, the optimal case would be if the distances are exactly equal. So I can try to express this with such a function f. So in the maybe this f could just represent that if these two distances are equal, then f is minimal, say 0. If the distances are not quite equal, then f is positive, yeah, has larger values. Now, why don't I just take the difference of these distances? I could just take xi minus xj distance minus yi minus yj distance, and maybe take the square of this, and then that could be my cost function. Well, the reason is then I would be trying to enforce something which is not really possible, namely then I would want that all the distances in the high dimensional space basically match exactly the distances in the low dimensional space, yeah? But I already told you this is normally not possible. So I need a little bit more freedom. So I will later construct this f in such a way that if the distances are small, then it's really important to me to keep them small in the projection. Whereas if the distances are large already, then I don't care so much. Okay. But suppose we have chosen such a cost function. Yeah? Then we can just apply what we already know from neural networks. Then we can just apply gradient descent. So then we can try to move around these projected points, the yi, in the low dimensional space along the gradient of this function in order to minimize this cost function. Okay. And so this first of all, this would be the gradient descent we apply. Very simple. This exactly the same as for the neural networks. So here I wrote it a little bit in the physics way. So the time derivative of a point in the low dimensional space would be minus the gradient of the cost function with respect to this point. Yeah? And so it would automatically try to minimize the cost function. All these projected points, the y, they would start moving around. And I will actually show you a movie in a moment to see how this happens. Yeah? But then you can also view this really from the physics perspective. You can say, oh, this looks like a set of particles, a set of points moving around in space that looks like a set of particles. And you will really see that sometimes these particles have attractive forces, namely whenever the high dimensional distance is very small, but here in the projected low dimensional space they are still far apart, then they obviously must attract each other in order to compensate for this, in order to also make their distance small in the low dimensional space. And this will be exactly what happens. Yeah? So you can interpret this as a set of overdamped particles where the force gives me the velocity that are moving around under the set of forces, and the forces are defined by my cost function. So they, in some sense, they derive from a potential energy. Okay. So the question is still how to pick this cost function in detail. And I will just briefly tell you about the choice that people made for this so-called tSNE. So first, what the letters SNE stand for, stochastic neighbor embedding. That sounds rather abstract, but the idea is the following. I want to imagine a process where I'm picking pairs of points, and I can label all the points by their index I. I'm picking a pair of points, and I want to set up a probability distribution for doing this that prefers points that are close to each other. Yeah? So that to choose in this way randomly a pair of points will become more likely if they are close to each other. I can set this up. I will show you a choice for this in the following. But so let's say Pij is the probability to pick a pair of points with indices I and j, and it will be chosen to be large if they are close. Okay, fine. And similarly, there will be some Qij. This is again a probability distribution, but now this is the one for the low dimensional space. Again, this will be large if they are close. And of course, these are probabilities, so they are normalized. And so what do we want to have? I said we could demand the distances to be close to each other, but what people do here is maybe slightly more abstract. So you have these probability distributions that in some way encode whether points are close to each other. If they are close, then the probability is higher to pick them as a pair. And now we want that these probability distributions are somehow similar to each other. They should be as close to each other as possible. So in the best case, it would be that if in the high-dimensional space, there's a 90% probability that I pick points 3 and 5, because they are really very close, then also in the low-dimensional space, there should be a 90% probability to pick the points 3 and 5 in this low-dimensional space. Yeah? And so it turns out, if you have two probability distributions and want to make sure that they are really close to each other, there's again a kind of distance measure to do this, and it's called Kullback-Leibler divergence. It's not really a distance; it's not symmetric in the probability distributions, but it's a very good in many contexts and also in this one. And so what you do here is very similar to what we discussed when we said categorical cross entropy to compare probability distributions with only slight changes. It's also obviously, for any physicist, it's obviously connected to an entropy as such. And so what you have is something like P log P over Q. Okay, so let's take that as a cost function. And then we still have to decide how do we choose the P and the Q. And remember, these should become large when the points are close. And so now these are the very particular choices that people make for this favorite t-SNE embedding. So for the high-dimensional space, they choose a probability distribution that's essentially the exponential of the distance squared. So it's like a Gaussian. If you go away, so in the immediate vicinity, very close to a given point, the probability will be high. If you go far away, then this Gaussian will drop off, and then basically you don't see it anymore. In the low-dimensional space, it turned out to be better not to do the same. You would have the option of doing the same Gaussian also in low-dimensional space, of course. But it's better to have another distribution. And this one, if you look closely, is basically the inverse of the square of the distance. So again, this will fall off for larger distances, similar to the Gaussian in high dimensions. But it doesn't fall off so quickly. Yeah? And so that's pretty important for this game. So remember, in high-dimensional space, obviously there's a lot of space in high-dimensional space. Yeah? So you can put a lot of points very close to each other without crowding. But in low-dimensional space, things become very quickly crowded. So it's very difficult to put them close to each other. Yeah? And so we must give these points a little bit more freedom. It should be okay even in the low-dimensional space, even if they move a little bit further apart. Then this should still count as a good match to the probability distribution in the high-dimensional space. And this is provided by this trick of choosing Q function for the low-dimensional space that falls off rather slowly. So even large distances are still quite okay. They are still considered as okay. Well, okay. And so if you now pull everything together, yeah, so the cost function in terms of the Kullback-Leibler divergence and these definitions of the probabilities in low and high dimensional space, what are these gradients? Yeah? Because these are the forces that really act on our cloud of particles. Well, and this is just a bit of mathematics you have to go through. And the reason I'm showing it here is, again, because it can be discussed in physical terms. So what's the force on some particle number I? Well, it gets contributions from all the other particles, so there's a sum over J over all the other particles, just like for Coulomb forces and so on. And then there are several terms. So first there's a term that determines the sign, and it will vanish if the high and low dimensional distributions exactly match, because that's the perfect situation. You cannot get better than that. Yeah? Then it will vanish, and then if these gradients are all zero, nothing will move anymore, and everything is stuck, and that's the final version of the point cloud. But unless that is the case, you get some term, and here the sign will depend on whether the distance is larger in the high dimensional space or lower dimensional space. So that's already good. And then there's a spring-like term that is very important at low distances. So for example, it could lead to two particles that are, 2 points that are very close in high dimensional space. They would have a spring-like attraction in low dimensional space until these terms here match and become 0. And then if they are further apart, there's this fall off, yeah? So you have 1 over the square of the distance. So together with a spring-like term, it still falls off, maybe sort of similar to gravity, roughly speaking. And that's, again, very important. If it were only for this first spring-like term, then for 2 points that are not sitting at exactly the right distance according to this first term, they would start moving very much, even if they are very far apart. So somehow even the long distances would matter very much in this game. And this is not something that we can afford to have, because I told you that it will never be possible to completely make the distances in the low dimensional space match those in the high dimensional space. We should be very happy already if the immediate environment, if the low distances match nicely. And so the second fall off is very important. So essentially it's telling us that, okay, if 2 points are very far apart in the high dimensional space, then I don't care. I can place them anywhere in the low dimensional space with respect to each other. It will be fine. Okay. And now I want to show you a few examples, and it's very nice to see these examples. And these are a little bit random. The first one is out of biophysics, so people recorded, actually it has something to do with neurons. They recorded the voltage traces of neurons, but that's not so much the point here. Each trace was then represented as a vector in a high dimensional space. And the question is, how do you visualize this? How do you visualize it in such a way that maybe you are able to determine clusters? Maybe there are some voltage traces of a certain kind and some other voltage traces of another kind. And how can you distinguish that just without just looking at it with your bare eye, but trying to feed it through such an algorithm? And so let me just switch to the video, because what these people did was they let this tSNE gradient descent run. And so what you will see is a point cloud of points that are moving around in this low dimensional space, trying to minimize the cost function that we saw. And you will see it's completely scattered in the beginning, but then slowly the clusters emerge. You see, now it finally understands it has to obtain some structure. And there's even more structure evolving now. And now you see some slow flows of points in this tSNE. And now it can take longer and longer. But you see the concept, yeah? So there's really this flow of particles determined by the gradients. And sometimes clusters can merge. This is obviously what's going on down here. But you're not guaranteed to always... So for example, one of the things I want to mention is you're not always guaranteed to get the same results. If you start with slightly different, say, stochastic initial conditions or a different piece of the initial data set, you might end up with quite different looking results. Because after all, this is a nonlinear technique, and small differences can have, as a result, a large change in the output. So you need to be aware the detailed shape maybe doesn't matter so much, but whether whether points are in a joint cluster or not, that can tell you something. So if you exercise a little bit of caution, then this is really useful. Okay. Here's another example without animation. So let's look at these image recognition databases. And so this was a neural network that was trained again on many training examples. It was a multi-layer convolutional network, the kind that we described for classifying images. And now you just take a few of the neurons, say in one of the hidden layers of this, maybe of the last stages of this neural network, and you try to do a tSNE on the values of these hidden neurons. So in this case, it says he applied it to a 4096 dimensional representation. So there are 4096 neurons. And you treat them as points in a, you treat the combination of all these neuron values as a vector in a 4096 dimensional space. And then for each picture in your training set, you will get a different point in this 4096 dimensional space. And the task of tSNE is now to project this down in a meaningful way to 2 dimensions. And then what he did is to plot each of these, to plot at least a few example images at the points that tSNE suggests. So if tSNE puts some training example up here, then you will also plot the resulting, the corresponding image you will plot there. And the funny thing is, if you look at it, it really makes sense. So you can try to spot what happens. For example, there was some corner in which there was a lot of vehicles, cars and trucks and so on, and maybe also houses and structures. And then there was another corner with a lot of animals. And so you can start to distinguish these corners, and that's really interesting. Remember, tSNE is not being told the labels. It doesn't know that these are cars or dogs and so on. But simply because the neural network tends to give a similar response to these images, you will also have tSNE placing them close to each other. Well, sometimes it goes wrong, so to speak. Here, there are some examples where obviously it doesn't get it quite right, but that's okay. Okay. Here's another very nice example, which I like a lot. So I hope you know about the archive. The archive is the biggest database of directly accessible scientific articles. So you just go there and download them for free. It has over 1 million articles, so this 1.3 million is already outdated. Sorry for that. So you just go there and see what articles people put up there last week, and then you can just download them and read them and don't need to pay anything. So now, however, this creates a problem, yeah? 1 million articles, no one can read them. How do you even find your way around in so many articles? And so there's a beautiful website that is called Paperscape. So what they have done is they have used techniques similar to tSNE in order to generate an automatic map of the whole archive and represent it as a 2D map. And this is not done by humans. I mean, the labels here are given by the human labels if you upload it into different categories of the archive. But where the points lie is only determined by, so to speak, the meaning of these articles. Each point is a single article. Yeah? And it's kind of similar to tSNE. It's not the same. It's actually more physically inspired even. And between 2 papers, that is between 2 points, there are 2 forces. First, there's always a repulsion. So if the articles have nothing to do with each other, automatically they will repel and distribute themselves evenly. But also, if 2 papers, if a given paper cites another paper, so the authors write, oh, in this earlier paper there was already something about a similar observation, then obviously they have something in common. They are somehow about the same topic. And so there's always an attraction between a paper and the other papers that it cites. And so this will automatically cluster together papers that are about the same topic. And then there are some details like avoiding overlap and so on. And so every morning, really, I don't know whether they still do it in this way, but every morning after the new papers come out, just a moment, they recalculate using this technique a complete map of the more than 1 million papers. Yes, please. Yes, they only need the references, and you have to see that, of course, they now incrementally they only need to download the new articles, obviously. Yeah. But then, yes, they have the full structure, so they know this paper cites 30 or 40 other papers, and so then there will be attractive forces between this paper and the 30 or 40 other papers that it cites. Yeah. But it's really very nice. And so let's zoom in. So this is the quantum continent. So all the papers that have something to do with quantum mechanics, quantum physics, often applied to things like quantum computing. And actually, this has been taken up by someone and turned into an artist's representation, because then you can zoom into the different areas and you realize, oh, this is the typical topic that they write about. This is, of course, done by a human, so this is not something that the computer automatically knows. But the fact that you are able to draw this map and extract these meaningful labels means that the algorithm has done a good job, simply by looking at which one cites which one. Okay. Good. Are there any questions about this tSNE or the paperscape? Well, if not, then let me go on. Okay. Okay, now I'm jumping to something more technical again. We're coming back to neural networks now that we know how to visualize them, maybe. And we ask ourselves, we had this gradient descent algorithm, which, as we saw, is also important in other contexts like tSNE. How can we speed it up? Because sometimes it really takes a long time to converge. And there are various techniques, but the most important thing is that you want to pick the learning rate in an adaptive manner. Yeah. So otherwise it would just be trial and error. You pick a learning rate parameter eta of 0.1 or so, and you see maybe it converges, maybe it doesn't, maybe it's very slow or maybe not. So this is not very nice. So it would be much better to automatically pick the learning rate. And this is also very similar to what people do when they solve differential equations. So when in physics you use a technique like Runge-Kutta to solve the equations of motion of the planets, let's say, then yes, there is the simple-minded version where you say what is the time step, but there's also smarter versions where the algorithm automatically can choose for you the correct time step. And when the two planets come very close to each other, then the time step is reduced because you need that for the accuracy. But if they go far away from each other, then you can increase the time step again and go faster. And so the question is, can we do something similar here to make the learning rate adaptive? And so over the years, really many different techniques have been invented for this. I want to go through a few of them just to show what's behind it. It's nothing really magic, but they are super useful. And so maybe let's start with a simplest version here, ADA-grad. So ADA means adaptive, obviously. And so what you start with is, well, here's the gradient that you want to talk about. So dc, the cost function dc over d theta j. Theta j is one of the many parameters, like one of the weights in the neural network. And just because I want to abbreviate notation, let me call this component of the gradient, let me call that gj. So g is the gradient. Well, and now the standard gradient descent would be written down like this. So I change the vector of parameters theta, by taking the old vector and subtracting eta times the gradient. This is very simple gradient descent. And then on top of that, this gradient we know is actually sampled stochastically from a small batch of samples and so on. So these are the other details. Okay. Now the problem is that maybe you don't know beforehand how large will be the gradients. Maybe the gradient is very small, the magnitude of the gradient vector is very small. And then if you multiply that with another small factor, that is the learning rate, 0.1 or so, maybe everything becomes super slow. And so people thought maybe it's better if we just kind of renormalize the gradient. Yeah? If we somehow take this gradient vector and, I don't know, divide by the magnitude of the gradient vector or something like this. And now you have to understand the following. So this is so each component of the gradient vector refers to one particular parameter. Yeah? So this is Gj is referring to this theta j parameter. It tells us how the cost function changes if you change theta j. And so it may be that some of these gradients are really large and others are really small. So in principle, if you do this adaptive thing, you even want to treat each of these gradients independently. Yeah? And so one thing that people came up with is, let's estimate a typical size of the gradient and then divide by that in order to renormalize things. And so what do we mean by typical size? Well, one way to try to estimate it is to take the square of the gradient. Here it's even the square of the component j of the gradient. Maybe sum over all previous time steps to get an estimate of how large this gradient is typically. And take the square root of this, even to just get the same dimensions as the g in the numerator, and divide by this. So this is something like the typical variance, yeah, the typical, well, the square, the root mean square actually, of this gradient component. And that's it, yeah. So basically you would divide the gradient by the root mean square of the gradient component. And if you want to be really cautious, maybe this is 0, but then maybe you add some epsilon because it sits in the denominator, so you don't divide by 0. Okay, so this is one of the simplest and earliest approaches. It doesn't really work great. The problem with this is if you have this sum over gradient squared in the denominator, this sum will grow over time, yeah, because you have more and more time steps to deal with. You will sum over the g square of all these time steps, and so the sum will grow, and so the overall size of your gradient will diminish, and maybe this is not what you want. And so then there is a modification. So someone says, well, that's obviously bad if the size of the step diminishes. That's not what I wanted. Instead of taking the sum over all previous time steps, maybe I just take it about the 10 last time steps. So then this will not happen. And if you want to make it a little bit more sophisticated, instead of taking precisely the last 10 time steps, you can do something like a running average where you diminish more and more the influence of very old data. And this can be done in a general way here. I point it out simply because it also will come up later in other contexts. So you say if capital V should be my estimate of the variance, so V is the thing where I will take the square root in the end, yeah? Then let me just say this. The V at the new time is some decay term times the old V, so for example 0.9 times the old V. So that would mean the influence of the old estimates fades away, plus 1 minus gamma times the new G squared. Yeah? And this is a way of accumulating an average, but also fading away the old input. And so you can also write down the solution to this. Basically, the V at any given time t looks like the sum over all previous times. But you know, in contrast to what we had before, the contributions from previous times are weighted by this weighting factor. So since gamma is less than 1, if I take gamma to the power of the time that has elapsed, then obviously the very old times, they will be basically set to 0 and they will not contribute to this sum. Okay, and that's basically the idea. And so then you have, you can do this root mean square only of essentially the last few previous gradients. And so then you would do the update like this. Instead of saying I change my parameter by eta times g, I change it by eta times g divided by the square root of this variance that you implemented in this way with a running average. Okay. I will skip this ada delta because now I want to come to the thing that most people use these days, which is very similar to what I had by now. So here the basic idea is not only do you do this running average of the variance that you use in the denominator to normalize, you also do a running average of the gradient in the numerator that you want to have on the right-hand side. So basically, if g is the present value of your gradient, you do the same thing as before. Now I have another parameter that I call beta. Again, it's a number less than 1. I take the old value of the mean gradient, beta times the old m, plus 1 minus beta times the new g. And so as a consequence, this m will effectively be not the present value of the gradient g, but something like an average over the last few g, slowly fading away. The v, the variance estimate, is like before. And then basically you do an update like here. So the new parameter is eta times this running average over the gradient divided by the running average of the g squared. And then, okay, these are little technical details. You just want to make sure that at the beginning of time you don't have any artificial things that come about because it's at the beginning of time. So you can believe that people figured this out correctly. And so this is Adam. And whenever you don't know anything else, you will typically use Adam nowadays. And the funny thing is Adam is not very old. Adam is just, if I remember correctly, from 2014. Yeah. So this is one of the amazing things about this field. Something as simple as Adam is only a few years old, as simple and basic and useful. This is similar to, I don't know, the early days of quantum mechanics when something like the Fermi golden rule was only a few years old. Okay, and just for fun, I zoomed into Paperscape because there's also a computer science part of the archive. And you see here Adam, and you see people like Adam because this circle is very large, which just means that a lot of people are citing Adam. Okay. So this was a little technical digression, just so that you know when you then go and use Adam in your neural network training, you know what's behind it. It's not very difficult, but it's very useful. Okay. So now let me start with a new neural network concept. What we had in the very beginning was, so to speak, your standard neural network, where every neuron in one layer is connected to every neuron in the next layer. We call them fully connected or dense neural networks. Then we already discussed a particular class of neural networks, the convolutional neural networks, where we exploit translational invariance, and they are great for images. Now I will come to yet another class of neural networks, and that is so-called recurrent neural networks. Those are the neural networks that have memory, and it's something about time evolution. So when do they become useful? Well, they become useful if your data is really something like a time series. And there are many pieces of data that are time series. Even if you think about a sentence or spoken language, this is a time series. Either on the microscopic level, the sounds, that is a time series. But also if you just do the characters or the words, this is also a time series because it's word after word after word. And then, of course, there are also many temporal problems like in control. Think of a robot that has to do one thing after the other, and then it has to move its leg and so on. So this is also a kind of a time series. Okay. So, how do we deal with data that is a time series? Well, one of the first things that you could imagine is, well, in time we also have translational invariance, which is often a good approximation. At least if your system is not externally driven, that then it means that one time point is intrinsically no better or worse than another time point. And so indeed, this is what you could do, and which some people do. And it's not a bad technique. So you could say, let me take my input time series, let me apply a convolutional network, and then let me get my output time series that tries to do something, give some answer to something, modify the time series. There's a little catch here, though. When you implement this convolutional network, you have to determine in advance what is your filter size. And the filter size effectively here will mean the memory time. Because if you have a filter size of 3, then for a given point in time, the response, the output of the network, will only depend on these last 3 time slots of the input time sequence. Now, of course, you can expand this. Either you can choose simply a larger filter size, or you can have many hidden layers, and if each of them has on its own a filter size, then of course it can expand the range. But in some sense, you have to choose ahead the size of the memory, so how long you can recall things. So if you want to have long memories with convolutional nets, this would be challenging. You would need large filter sizes, and you would need to know in advance how you want to set your filter size. You can do tricks, and people are doing tricks like, for example, having something similar to what we did for convolutional networks for image recognition. So you use something like subsampling, so you reduce the resolution and then maybe you increase the resolution again and so on. So these are choices, but let's now talk still about the challenge of having really a long-term memory. And so what I mean by long-term memory is something like this. Here's a time series, and to make it simple, I will always in the following assume discrete time slots. So time is discretized. And then maybe my little robot gets a signal at some point in time. Then there are, for a long time, no important signals. And then finally, at a later time, it wants to recall what it was told before. And that's the challenge we are facing. So you need a long-term memory. You need to hold something in memory for a long time, and then suddenly you recall it, and you need to use it. And an example could be if the time sequence is really sentences composed out of words, then maybe you are being told a story. And then at the very end of the story, someone asks you a question about the content of the story. And they ask you, okay, which color was the ball that the cat was playing around with? And then you need to remember what you had been told 5 sentences before. And people do test neural networks on such stories. So, okay, so how, what to do? So you want to have this long-scale memory. And the solution that already comes from the 80s, 90s is called recurrent neural networks. So first I want to show you the general way how you would have to imagine these networks, and then I will tell you that there is a challenge, that there's a problem with them. So again, for the moment, let's imagine that each circle is just a neuron. Later it will get maybe more complicated. And these are the inputs. But now I'm really unfolding this in time. So this input neuron would hold the input at some given time, that would be the input at some later time, and so on. So each new circle represents one later time step. And then maybe I can calculate, maybe even in one single step, the output at a given time. Okay, fine. But if I only did this, if there was only this connection represented by the upward arrow, then each output would only depend on the input at that given time. That would be a little bit too simple. Yeah. So it's surely good enough for some tasks, but not for those where you really need memory. And so the idea behind a recurrent neural network is that you want to keep some memory. So the output is not just transmitted to the outside world, yeah, but you also keep part of the output to be available in the next time step. And then you can imagine things like taking both the input and the previous output in order to calculate the eventual output of this neuron. Yeah? So again, as before, these arrows represent connections between neurons, but now your input is no longer just the input that comes from the outside, but also the old output that was there in the previous time step. And so then in principle this could go on. So you could have all these horizontal connections which are along the time axis, which would mean that you keep some memory. Okay. So these individual circles do not need only to represent a single neuron. They could also represent a whole collection of neurons, in other words, a layer. Yeah? And then what I'm writing here is basically a layer of input neurons. You get all the connections that we know of. So if there are 5 input neurons and, I don't know, 3 neurons in the output layer, that would be 3 times 5 connections. So represented by this arrow. And then there are also connections between all these neuron values and all those neuron values when you advance by one time step. So that means any given neuron here would get input from all the neurons in the previous time step and all the neurons in the present time step that represent the input. Okay. Important is the following. So the weights, that is, so to speak, the strength of these arrows, they would be independent of time. Yeah. So we would not say that that these weights change in time. They would always be the same. Also, the weights related to the arrows that connect subsequent times, they would also always be the same. So that's a massive simplification. That's similar to the convolutional neural network, where we exploited translational invariance to make sure for one filter kernel we only need to store, I don't know, 3 weights, and then we reuse them on the whole image because of translational invariance. The same is true here because we have translational invariance in time. Okay, fine. So you might think this could work. It could work in the following way. I train on many input sequences. I tell the network what would have been the correct output for this particular sequence. And then I try to adapt my weights in order to make this happen, just like before. This is our concept all the time. We give a lot of training examples, the input and the corresponding good output, and we try to drive the network more into the direction of giving us these correct answers. So is this already the solution, is the question. And you could go on and on, so this is this would then become a hidden layer, this would become the new output layer, and so on. So how would training work? Let's talk about this for a moment, because that's where the challenge arises. Let's assume for a moment only the final time step gives us an answer. This is where our neural network should provide the correct answer. And we will later come to a very simple example that you can also program as a homework. Imagine that the input is a series of characters that represent digits or arithmetic signs. So like something like 32 plus 17, so 3, 2 plus 1, 7. These would be the inputs at the different time steps. Yeah, so these digits would be the inputs. And then at the last time point, you would want to have the result of this arithmetic operation up here. This could be a simple training task. So you would give many such sequences, and you would always give the correct answer, of course, because that's training. And you want that the correct answer is output here at the last time slot. Okay. So how to train? Well, it's in principle just exactly the same as we always did. So you know the correct answer. You also know the answer that the network is giving. You take the difference and take the square if that is your cost function. And you try to take the gradient of this cost function with respect to all the parameters in the network. And taking the gradient here, well, that's again applying the chain rule. Yeah? So basically you start by taking the gradient with respect, the gradient of the cost function with respect to this last output. But then you get gradients with respect to everything that is connected to this output. So in a usual neural network, you would just go down the different layers. We discussed this when we discussed backpropagation. Now you also need to go backward in time. So these are the horizontal connections. And so I tried to represent this by these two green arrows. So now the backpropagation will go both down in the layers and also back in time. Essentially, you have to differentiate with respect to everything that could have contributed to the answer, obviously. Yeah. Okay, so this is sometimes called backpropagation through time. So conceptually, this is fine. This works. But there's a challenge. And this was recognized in the 90s. So the challenge even has some nicknames like exploding gradients or vanishing gradients. And the problem is really what happens when you try to backpropagate through so many layers or through many time steps. And remember what really happens during one backpropagation step. So we are always carrying around with us this vector that I sometimes call deviation vector. So we start by initializing the vector in the last layer, and then we go down layer by layer. And whenever we go down one step, we really multiply this deviation vector by a matrix. The matrix contained the derivatives of this nonlinear function and lots of stuff. But essentially, it's a matrix vector multiplication. So each layer of backpropagation, each step in the backpropagation is a matrix vector multiplication. And so here, if I have a deviation vector at some time t, I multiply by a matrix, I get the deviation vector that would be responsible for the neurons in the preceding time step t minus 1. And so then what can happen is quite obvious. If you repeatedly multiply a vector with some matrix, there's the danger that the matrix contains large eigenvalues. Yeah? And so there will be components of this vector that repeatedly get multiplied by large numbers, because that's what happens. If you think of a vector decomposed in terms of the eigenvectors of the matrix, then multiplying the matrix onto this vector means that every component is multiplied with its own eigenvalue. And if some of the eigenvalues are large, that's dangerous. And if it happens repeatedly, then you get repeatedly multiplied by large values. And so what can happen is really that as you go through backpropagation, your deviation vector, the magnitude explodes, because there are some directions that simply grow. Likewise, it could be that there are some directions that correspond to very small eigenvalues. And then you repeatedly multiply by very small numbers, and then the gradient vanishes. And so both of these are really bad, actually. And so what this means is sometimes it could happen that whatever you try to do down here, it has no effect on the output. That's bad, yeah, because you try to change the earlier time behavior, it has no effect on the output. That's bad. But also it could be that the tiniest changes here have drastic significant changes in the output, and maybe that's also not what you want. And this was the typical kind of behavior that people encountered when they tried these recurrent neural networks. So the situation was bad. And so then finally, this was solved. I think either it was the diploma thesis or PhD thesis of Sepp Hochreiter. And the solution is called long short-term memory, LSTM. So you will encounter this if you look into recurrent neural networks. First, I have to explain the name. So, and then maybe I stop for today, but the name is worth to be explained. So when we think of even a standard neural network, in some sense has a memory. In the sense we are training it on many training examples, and so we are changing the weights, and somehow these weights carry the memory of all the training examples. If I had chosen different training examples, the weights after training would look different. So this is real long-term memory. This is as if I learned to do linear algebra 20 years ago by doing many, many exercises, and this is in the long-term memory. Yeah, okay. So this is one thing. But this is not the kind of memory we try to talk about here. Here we talk about memory that is not stored in these weights, but really memory that you can use during one single time series. So again, in the way that I described it here, maybe there's a signal at an early time, then there are many time steps without anything important, and later you need to recall this memory. So in that sense, this is called short-term memory. This is the memory that I'm using to solve some given task. In human timescales, this would be the memory on a minute or second timescale even, yeah, instead of the year timescale. But then if we want to have successful recurrent neural networks, we still want this short-term memory to be comparatively long. Instead of forgetting everything after a few steps, I want to have this memory be relatively long. Yeah. And so this is the meaning of long short-term memory. And I will just give you the qualitative idea first, and then next time we can discuss how it's really done. So the idea is basically that most of the time you will not need a given memory cell, a given memory value. Yeah? So most of the time maybe you should not touch it, you should leave it alone and don't do anything. And as it turns out, then if you don't do anything, this also means that this dramatic behavior with the exploding or vanishing gradients doesn't happen, because not doing anything in this language will be multiplying by 1, and that is harmless. Okay. And so how to make sure that this is so, we will add neurons that tell our memory whether it's time to read out something or whether it's time to write in something or to delete the memory content. But if these neurons say, no, no, don't do anything, then it's also fine. Yeah, then nothing will happen. And so this was the big breakthrough, to bring in these extra neurons that tell us whether something should be done with the memory, and if they say no, then nothing will be done with the memory. Okay, so is there any question already about this? This is just the concept, but next time we will explain how it works. Well, if not, okay, so then see you next time. Thank you.